Welcome everyone to the What Happens When channel, where everyday questions are answered. Before we get into it, why don't you hit the subscribe, like, and smash the notification bell? Okay, let's do this. Lightning strikes on aircraft have long captivated our imagination and sparked concerns about aviation safety, yet the reality of these dramatic encounters reveals an impressive triumph of modern engineering and human ingenuity. Today, we'll delve deep into the fascinating world of aircraft lightning protection, exploring how these magnificent machines keep passengers safe even when nature unleashes its most powerful electrical displays. Picture yourself cruising at 35,000 feet when suddenly a brilliant flash illuminates the cabin. While this scenario might seem terrifying, commercial aircraft are struck by lightning approximately once every 1,000 flight hours, making it a relatively common occurrence that rarely leads to any significant issues. The secret lies in the sophisticated engineering principles that transform these massive metal tubes into virtual flying Faraday cages. Let's begin by understanding what happens during a lightning strike. When lightning connects with an aircraft, it typically strikes a protruding part such as the nose or wingtip. The electrical current doesn't penetrate the aircraft's interior. Instead, it travels along the exterior skin of the aircraft, seeking the path of least resistance. This phenomenon occurs thanks to the principle of electromagnetic shielding, where the metal fuselage acts as a conductor, allowing the electrical charge to flow around the aircraft's exterior before exiting through another extremity, usually the tail or another wingtip. The engineering behind this protection system is remarkably sophisticated. Modern aircraft incorporate multiple layers of lightning protection, starting with the exterior skins. While many people assume planes are made entirely of metal, modern aircraft actually utilize a significant amount of composite materials, particularly carbon fiber reinforced polymers. These materials, while lighter and more fuel-efficient than traditional metals, present unique challenges for lightning protection. To address this, manufacturers incorporate a fine mesh of conductive materials within these composite sections, ensuring continuous electrical conductivity across the entire aircraft surface. But the protection doesn't stop at the surface. Critical systems within the aircraft are shielded through a concept known as electromagnetic hardening. This involves protecting sensitive electronic equipment through multiple redundant systems, surge protectors, and specialized shielding materials. The fuel tanks, which might seem particularly vulnerable, are designed with sophisticated protection systems that prevent sparks from igniting fuel vapors. Every wire, every component, and every system is carefully engineered to withstand the enormous electrical currents associated with lightning strikes. The testing procedures for aircraft lightning protection are equally impressive. Before any new aircraft design is certified for commercial flight, it undergoes rigorous testing in specialized facilities. These tests simulate lightning strikes of varying intensities, ensuring that all protection systems function as intended. Engineers use sophisticated equipment to generate artificial lightning bolts carrying hundreds of thousands of amperes, subjecting aircraft components to conditions that exceed what they might encounter in actual service. When a lightning strike occurs, pilots follow established procedures to ensure the aircraft's continued safe operation. While modern aircraft can typically continue their flight without issue, pilots perform thorough systems checks to verify that all equipment is functioning normally. They also report these incidents, contributing to a valuable database that helps engineers continually improve lightning protection systems. The statistics surrounding lightning strikes on aircraft reveal the effectiveness of these protection measures. In the entire history of modern commercial aviation, lightning strikes have caused remarkably few accidents. This safety record is particularly impressive, considering that commercial aircraft worldwide experience lightning strikes thousands of times each year. The last commercial aircraft crash in the United States attributed to lightning occurred in 1967, leading to enhanced protection standards that have proven remarkably effective. Understanding the physics involved helps explain why aircraft lightning protection is so successful. When lightning strikes an aircraft, the electrical current typically ranges from 30,000 to 100,000 amperes. While this might sound alarming, the aircraft's conductive skin disperses this energy across its surface, preventing any single point from experiencing dangerous levels of electrical stress. The entire event typically lasts just milliseconds, though passengers might perceive a longer flash due to the aircraft's movement through the electrical field. Let's explore some of the specific components that make this protection possible. Static wicks, those small, pointed devices you might have noticed on aircraft wings and tail surfaces, play a crucial role in dissipating electrical charge. These devices help prevent static buildup during normal flight and provide predetermined exit points for lightning strikes. The aircraft's radome, the nose cone housing important radar equipment, incorporates special conductive strips that channel lightning safely around sensitive electronics. The fuel system presents particular challenges in lightning protection. Modern aircraft employ multiple safeguards to prevent lightning-induced sparks from igniting fuel vapors. These include specialized fuel tank inerting systems that reduce oxygen content in fuel tank vapor spaces, conductive materials in fuel lines, and carefully designed electrical bonding between all aircraft components. Every fuel tank access point, every fuel line connection, and every vent is engineered with lightning protection in mind. The aviation industry's approach to lightning protection exemplifies the concept of defense in depth. No single system or component is solely responsible for protecting the aircraft. Instead, multiple layers of protection work together to ensure safety. This redundancy extends to the aircraft's electrical and electronic systems, which feature backup power supplies, isolated circuits, and sophisticated surge protection devices. The advancement of lightning protection technology continues as aircraft designs evolve. The increasing use of composite materials in modern aircraft has driven innovation in lightning protection systems. Engineers have developed new materials and techniques, such as embedded metallic foils and specialized conductive coatings, to provide the same level of protection as traditional metal structures while maintaining the weight advantages of composite materials. Weather radar and lightning detection systems add another layer of protection by helping pilots avoid the most severe thunderstorms. While aircraft can safely handle lightning strikes, avoiding them altogether remains the preferred strategy. Modern weather radar systems provide detailed information about storm cell intensity and movement, allowing pilots to plot courses that minimize exposure to lightning-prone areas. The human element in lightning protection cannot be overlooked. Pilots receive extensive training in thunderstorm avoidance and procedures for handling lightning strikes. Maintenance technicians are trained to inspect aircraft for signs of lightning damage and perform necessary repairs. This combination of advanced technology and human expertise ensures that lightning strikes remain more of an inconvenience than a serious safety threat. The development of lightning protection systems represents a remarkable achievement in aviation safety. These systems have transformed what was once a significant hazard into a manageable risk, allowing commercial aviation to maintain its position as one of the safest forms of transportation. The success of these protection measures demonstrates the aviation industry's commitment to safety and its ability to overcome complex engineering challenges. Looking to the future, research continues into even more advanced lightning protection systems. Engineers are exploring new materials and technologies that could provide enhanced protection while further reducing weight and improving fuel efficiency. The lessons learned from aircraft lightning protection have applications beyond aviation, influencing the design of other structures and vehicles that must withstand electrical strikes. The story of aircraft lightning protection is ultimately one of human ingenuity triumphing over natural forces. Through careful engineering, rigorous testing, and continuous improvement, we've created flying machines that can safely withstand one of nature's most powerful phenomena. This achievement stands as a testament to our ability to understand, adapt to, and overcome environmental challenges in our quest to master the skies. As our understanding of lightning protection continues to evolve, new technologies and materials will undoubtedly emerge to enhance aircraft safety further. Yet, the fundamental principles that have served so well for decades will remain at the core of these developments, ensuring that air travel remains fast and reliable, even when nature unleashes its most spectacular electrical displays. The next time you're flying through stormy weather and glimpse a flash of lightning, remember that you're protected by one of aviation's most impressive engineering achievements. What might seem like a frightening moment is actually a demonstration of human innovation at its finest, allowing us to continue our journey through the skies with confidence and security. Thanks for watching.